In this lesson, we're going to continue our discussion about random effects and kind of get the ANOVA table and how we test. Then I'll talk about how you can generalize it. In our last video, we talked about the food supplement example and we went into a lot of detail. In this case, let's just quickly review what our example is so we have something to refer back to. So here we're trying to measure calcium in food supplement. We were told that there are a lot of different possible labs and number of chemical calcium assays for calcium. Okay. We're also told that we're going to randomly sample 3 labs and 3 assays to perform our analysis. This right here is creating that random effect. We don't have 3 predetermined assays or labs. We're randomly selecting the 3 labs and 3 assays from their population, okay? Then we have this statement right here, where it says each lab combination is randomly assigned to 2 of the 18 prep samples. This green highlighted statement is just good design of experiment protocol. What we're saying is once we have our treatment combinations, we're randomly applying it. That is very familiar. We saw that in our CRD, our block, our RCBD, and all that. This green statement is just good design protocol. The underlined black statement is really telling us that we have a random effect. Okay, so let's introduce some terminology. So factor A will have A randomly selected levels. Factor B will have B randomly selected levels. Our total number of treatments will be A times B. If we come back up here, we had our total number of treatment combinations is 9 because we have 3 assays, 3 laboratories. But we also have to remember we have replication represented by little n. And so our total number of experimental units, capital N, is the number of replicates times the total number of treatment combinations. Okay? Our statistical model should hopefully look familiar, but our terms now are a little bit different. Okay, so we have our Y, which is our response, where I is going to go from 1 to A, J is going to go from 1 to B, and K is going to go from 1 to N. Our mu is still our grand mean response, but now what we have are random effects. Prior to this, when we were talking about our fixed effects, we normally had AI is a fixed effect due to treatment, and we wouldn't have this extra part right here. But now, we now have that our alpha I is a random effect. Our beta J is also a random effect. And the interaction term, because both of these are random, is also going to be random. Okay. Now, typically in our past videos, I've kind of went quickly on this section, but there are a couple things that I want to make sure to point out. So previously, when we were only talking about fixed effect, our only random term was this. And we had our normal 0 sigma squared epsilon, and we would try to estimate this, and we would use MSE to estimate this from the ANOVA table. Okay, but now since we have randomly selected the main effects in the context of our problem, that's with the lab and the assay, and then our interaction effect, we now have random distributions that we set for each of these terms. So that's what this is saying right here. Okay, and so we now have to estimate these variances as well as this one. Okay, so the idea of having multiple variance components should hopefully look familiar because we did talk about multiple variance components in our subsampling lesson prior to our midterm. In the subsample lesson, we broke up our epsilon, this variance, into two parts, but now we're breaking it up so that our main effects have this extra variance component. The idea of this variance component is going to become more important as we move on and talk about inference, how we do follow-up analysis, and our hypotheses. But I just want to point out to you that we have these multiple variance components. With our random effects, because we have these extra variance components, our expected response and variance for each response is a little bit different. So for each response, i.e. the yijk's, we expect the mean to be mu and the variance to be sigma squared y. Sigma squared y is going to be decomposed from the variance components that we just talked about, okay? How we get this is if we look at this model up here, this y equals mu plus alpha plus beta, the interaction term and the error. If we take the expectation across this, so we take the expectation of yijk, this is going to be the expectation of mu plus the expectation of alpha. I'm going to drop the I just for simplicity. Expectation of beta, expectation of alpha, beta, and the expectation of epsilon. I drop the subscripts just for simplicity. We know there is no random distribution on mu. It's a constant. The expectation of a constant is the constant. And so let me grab another pen. So the expectation of mu is, that's hard to see. Expectation of mu is mu. Now, when we look at the expectation of alpha, beta, and epsilon, we can see that they're coming from a normal, 0, and their variance component. So the expectation, i.e. on average, if we kept collecting our alpha i's, we'd expect it to be 0, 0. Expectation of our interaction is 0, and the expectation of our random effect is 0. And so really what this results in is this y, because this mu, because everything else is 0. For our variance term, yijk, similar idea, the variance of mu plus the variance of alpha, variance of beta plus variance of alpha, beta plus the variance of epsilon. Now, the reason I can write the variance term like this and not have an extra term of the covariance is because we're assuming that all four of the random components are independent of each other. If we didn't have this assumption, this variance equation isn't true. If you go back to your stat 5615 notes, hopefully they mention that. If not, and you're interested more on where this comes from, we can talk about it in office hours or a review session. Okay, so the variance of a constant is 0. And then when we look at the variance of alpha, beta, our interaction and our epsilon, it's just coming from these terms right here. So what do we expect the variance to be? It would follow these terms, and that's why our variance of our y is equal to the epsilon. If you didn't completely follow this, or you haven't taken a previous stat class that talks about expectation and variance, this might be a little bit confusing. You don't need to know the whole steps behind this, but for those that are interested, we have it and try to give some explanation on what's happening. Okay, so what is the difference? So if we're just thinking about fixed effects models and random effects models, how are they different? Well, in a fixed effect model, each response has the mean of mu plus alpha I plus beta j plus our interaction. And the variance is just sigma squared epsilon. Okay, in a random effects, our response has an expected value of mu, and our variance, an expected variance of all of the variance components. Okay, so in fixed effects, the treatment effect acts as a component in the mean, i.e. that's what I'm talking about there. And in a random effects model, the treatment effect acts as a component in the variance. That is that we see it here. Okay. So with that, it's going to automatically, hopefully noticing that our mean and our variance and where our treatment is in these will hopefully give us some, giving us some intuition that our hypotheses won't be the same. So let's look at our hypotheses. First, let's remind ourselves of what our hypotheses were in the fixed effect model. So kind of all the lessons up to here. So up until now, in a fixed effect model, we were looking at our null of alpha 1 through I, where I is fixed, okay, versus the alpha i's not equal to 0 for some I. Simpler way was the treatment has no effect versus the treatment has effect. Now, we don't have these fixed 1 through T sets anymore. Like we're not only just focused on T treatments. We're trying to make an inference for the overall population variance. So with that, our hypotheses are going to be in terms of the variance component. So for a random effect model, rather than worrying about the individual treatments, we're worried about the variance, the overall population variance. And how we write that out is sigma squared alpha is equal to 0 versus sigma squared alpha is greater than 0. The reason why this isn't not equal is because variance needs to be positive. So this has to be positive. And again, we're not interested in the individual treatment effects, but the population variance. We're going to talk, in a bit, we'll talk about the new conclusions we have for this. But I want to start with our ANOVA table and how our ANOVA table and our test statistics differ. So in our ANOVA table, if we were looking at it, our degrees of freedom, our sums of squares, and our mean squared are the same. What I mean by that is that you would calculate them the same way you would in a two-way factorial design. The reason in this case we would treat it as a two-way factorial design is because of our problem. Our problem essentially breaks down to one treatment, two treatment, and we applied a CRD design. So this is a factorial design where we have two random effects. So our degrees of freedom, our sums of squares, and our MS for how we would calculate them would be the same as how we calculated them in our factorial design in lesson 7. Okay. What differs is the expected mean squared, because now some things are random and some things aren't. So in our fixed effect, we've seen these MSEs before, or the expected mean squares before. Now, in a random effect, our expected MS or our mean squares are different, okay? And so now this means we need to go back and figure out what is the right F stat for the interaction A or B, okay? So let's look at this. When we are looking at the fixed effects and trying to figure out what denominator use, so note, fixed effects, we had, let's say, if we were to test F stat or compute it for A, we'd look at the MS of A over the MSE. We did that because the null hypothesis would take this, cancel it out, and we'd be left with sigma squared epsilon divided by sigma squared epsilon. And that's how we got our MSA over MSE, at least the intuition behind it. We're going to keep that intuition for here. But instead of using this column with fixed effects, we're going to be using random effects. Okay, so let's first look at the test for the interaction effect. So we have our interaction effect here, and we know that our our hypotheses would be looking at sigma squared AB equal to 0 versus the alternative sigma squared alpha beta greater than 0. So under the null hypothesis, we would expect this to go to 0. So we would expect this to not be there. Then that would leave us with these two terms. So we know the correct F stat for the interaction effect will be MSAB, this term, divided by our MSE. Okay, giving some intuition there. For our main effects of A or B, let's look at A first. We know that our null will be sigma squared alpha equal to 0 versus alpha A, or not alpha A, alternative hypothesis, sigma squared alpha greater than 0. Okay, we're going to come up here to look at our random effects, and what we're going to see is under the null, this would be 0. And so this chunk right here would be canceled out. And we would be left with sigma squared epsilon plus n times sigma squared alpha. Okay. Now our thing is we want to see where else we would see this. Unfortunately, I crossed this out to explain this part, but notice that the expected mean squared for our interaction is that yellow term. And so when this goes to 0, these would go to the same, you'd get that 1. And so that is why our denominator for our main effects of A is MSAB. The same thing applies for our main effects of B. Our null hypothesis would be looking at the sigma squared equal to 0 versus our alternative, sigma squared beta greater than 0. This would get canceled out, and then we would have this yellow term divided by that. And so our MSAB is on our denominator, okay? To put this in nice, kind of quick, simple format of our hypotheses and test statistics, I kind of made us a little chart right here, okay? Some of the major takeaways. First, our test statistics have different denominators. How we figured out what denominator to use, we used the expected MS, the mean squared. Okay, so for our test of interaction, our denominator is MSE. For our main effects, it's MSAB, okay? Second, with random effects, we're interested in variability and not just the individual treatment effects. We'll talk more about, and then third, which we'll talk more about in a second, / foreshadowing. But with random effects model, we don't have to test the interaction first to then move on to the main effects. If we're in a random effects analysis and our interaction term is random, then we really just care about the component of variation from each piece. So there isn't a protocol like we've seen in our factorial design where we have to look at the interaction first and then we have to move or not move to our main effects. We'll talk more about that, but foreshadowing a little bit. Okay. Our homework will hopefully also get you guys into the practice. So what are some comparisons between fixed effects and random effects? In a two-way fixed effects model versus a two-way random effects model, keeping it pretty simple right now, what is the same? The summary statistics are the same. The sums of squares, the same. The test of interaction, the test statistic for the interaction is the same. That is MSAB divided by MSE. Okay, but what is different is how we write our hypotheses, our expected mean squares, and then our test statistics for our main effects. The big difference is now that our denominator is now MS of the interaction, okay? It also is going to allow us to have a broader scope of inference, okay? And let's kind of quickly talk about that. In a random effects model, we're no longer interested in estimating individual treatment effects. We don't care about maybe treatment 1 compared to treatment 2, compared to treatment 3, compared to treatment 4, or even just estimating individual treatment effects. Because we're not interested in estimating individual treatment effects, then there's no point of doing a multiple comparisons or those contrasts, okay? What we are interested in is estimating that variance components seen here, okay? Let me repeat that one more time because it can be a little bit tricky. With a random effects model, we're not interested in looking at the individual treatment effects. Because we're not interested in the individual treatment effects, there's no point in comparing through maybe Tukey's or Fisher's or another common one I don't think we talked about, Bonferroni, whatever, or using contrast to look at the differences of the individual treatment. In a random effects model, we are interested in estimating these variance components and looking at the overall population. Okay. So there's also some testing protocol, or there are, but isn't. Let me explain. In our fixed effects model, when we were talking about a factorial designs, lesson 7, if our A-B interaction was significant, then our main effects test on A and B may not be appropriate. Remember, it may not be appropriate if we saw masking or stuff like that. So we had to be careful. If our interaction was significant in a fixed effects model, we had to be careful on whether we could move to our main effects. In a two-way random effects model, even if our interaction is significant, so we conclude that our variance is greater than 0, we can still explain the variability in the population of the treatment effects. So the main effects tests for random effects are, I'm going to put this in capital, always appropriate. For our fixed effects, they may not be appropriate, but for our random effects, they are always going to be appropriate. Okay, now we've talked a lot about variance components and the population, but we also have to know how to estimate these variance components. So the last portion of these notes looks at our how we would estimate them. Really, it's just kind of plugging it into these formulas and going about our day. So to estimate our epsilon, it's still MSE. To evaluate our sigma squared alpha, or of our interaction. It's our interaction minus our MSE. For our alpha, it's MSA minus MSAB. And for our beta or B, it's MSB minus MSA. And then just always be careful to look at what the denominator is. Now, mathematically, it is possible to get a negative variance because we could have an MS of our interaction larger than our MSA. So that would induce a negative variance. However, we know variance cannot be negative. That doesn't make sense. So when you get a variance that's negative, the default is just to put it at 0. It's pretty much saying that it's really not having an impact on our analysis. One way we can look at how much impacts certain variances have compared to everything else is by kind of decomposing it and looking at the proportion of variability due to each effect. Okay, now this isn't a formal statistical test, but it can at least maybe tell us where most of our variability is coming from. So this is just working with proportions. All right, so recap, this lesson focused on looking at the ANOVA table and the hypotheses and the difference between a fixed effect analysis and a random effect. Some of the major difference, the hypotheses for the tests are different. We're now looking at our variance, okay? Also, our test statistics for our main effect are different. Our denominator for our main effects is MSAB, where for the interaction, it's still MSE, okay? That's important. Our protocol for testing, another big difference we want to be careful to remember is that even if the AB interaction is significant, we can still always test our main effects because our variances can still explain the population for the main treatment effects. Okay, to get a better grasp and continue to understand this a little bit better, we're going to move into our next video, which will show the analysis for our food supplement example.